Welcome all of you. Since last couple of classes, we extensively discussed varieties of 2D techniques. Especially in the last class, 1 or 2 classes, we discussed NOC, conceptual understanding, varieties of 2D NOC experiments, where it could be like steady state NOE, ROSI, heteronuclear overhauser effect, transient NOE using 2D. 2D is the transient technique. I told you in the previous class, 1 or 2 classes before itself, I said it's a transient technique. So there are varieties of things we discussed. In the previous class, we took large number of examples to analyze and get the conformation of the molecules by using combined use of varieties of 2-dimensional techniques like COSI, NOC, HMBC, HSQC, etc. Basically, at the end, NOC was used to get this conformational information and also to get the information about the substituent in different places in a given molecule based on the correlation information we obtained from the NOC spectra. Lot of examples we took, and in a given molecule there could be cis geometry, trans geometry, or both could be present. I took all these examples and we analyzed the spectrum, and fairly we were able to easily we were able to get almost geometry, structural conformation of all these molecules by using NOE correlations. One has to be very precise and one has to be very careful, and of course how you do the NOC experiment for the 2D is very easy. I mean, you don't need to worry too much about it. Of course there are certain complications which I discussed already, we can take care of it. But one problem with the 2D NOC is it will take a lot of time, and also depends upon the mixing time and everything. You have to set the properly mixing time so that there is enough time for the spins to transfer magnetization between themselves, which are NOE coupled. Fine. But I'd say, let me say I have a small molecule, not like a big protein. By mind you, I wanted to tell you this NOC technique. I showed simple examples to make you comfortable. I see if I have to analyze a protein spectrum or a big molecule, to analyze NOC spectrum itself will take several hours. Every cross peak we have to identify and then start getting the information about the spatial proximity, structural information, and finally the distance information. So that is a huge task. That is only if you are in that field, if you are working on a particular molecule, you will spend several hours, several days and weeks to get the structure. That's fine. That's why I took only small, simple molecules to make you comfortable. Even then, let us say, if your fairly big molecule you are doing, if you are a biologist or a biophysicist, a biochemist, you have a fairly big protein you are trying to work on, and then you are getting a very good NOC spectrum, let us say which containing several hundreds of cross peaks. That's fine. For such molecule you have to do that. But you are a small molecule, let us say. We don't require that much time. You don't have to acquire in a 2D data, spend hours of several hours of experimental time. And if it's a simple spectra like we saw in some of the previous examples of the NOC, can we do the same 2D experiment in a one-dimensional way? That's what I said, steady state NOE. Selectively we can excite one of the protons. That's what I told you. And then apply equivalent RF power, identical RF power, far off resonance, far off from the region of interest, and then take that as a reference spectrum. Take the difference between the two. If there is an NOE, you will see the enhancement of the signal intensity. Whether it is positive or negative is a different question. You are going to see that by taking the difference. And of course, that is if it is a simple molecule like in the previous examples we saw, there is only one. If you want to find out whether it is cis or trans, and if you have made the assignment by a simple 1D or a COSI experiment, why do you have to spend time to do the NOC? Can you not do in a 1D way? See, many of these 2D experiments like TOXI, NOC, HSQC, ROSI, all these things can be done in a one-dimensional way. You don't need to go for 2D also all the time unless there is a pressing need for it. So I will show you how we can utilize one-dimensional NOC technique to get the structural information in some of the molecules. We will start with that work today. This is called selective NOE experiment, also called steady state NOE experiments. I discussed this when I was discussing the concept of NOE and varieties of NOE experiment. Steady state NOE experiment is very simple. You apply a pre-saturation RF power, small pulse, small RF pulse for pre-saturating the selected signal of your interest. Apply 90-degree pulse, start collecting the signal. That is a very simple one. Of course, I told you, you have to carry out the difference experiment. Selectively saturate a proton by very low RF power for a time t, collect the spectrum. Identical experiment you do, apply same RF power far off place for the same amount of time, so that intensities are not getting perturbed because of RF power. Even if there is a perturbation, it should be equal for both of them. Collect the spectrum. That is what I said, and this is the reference spectrum. Now take the difference between these two. This is what I told you in the steady state experiment. If you do that, difference of that, if there is NOE, you are going to see it. This is all the steady state experiment you can do. Very simple experiment. And of course, lot of things about selectivity of the particular frequency, and then uniform perturbation of the multiplets, everything, all complications. If you do not do, what will happen, we discussed. So, in the steady state experiment, selectivity of the frequency for saturation is very important, pre-saturation. Assuming that you are all comfortable with that, you know how to do the experiment. Let us look at the applications of some of them by using 1D steady state NOE. I am going to discuss couple of applications today. One is you can identify E and Z geometry in the alkene isomers. Already we saw in the 2D NOE, finding out cis and channel geometry. We can find out aromatic substitution position, that also we saw. We can make the resonance assignment, that is very important. You can identify while making the assignment, if you get a doubt whether this proton is this or the other one, which is the resonance frequency for a particular proton, then at times NOE also comes into picture, and then conformational preference if there is any. All these things can be addressed. Anyway, there are many more applications. I am just trying to show you one or two applications where by doing one dimensional selective NOE, you can always address some of your problems, some of your research interests. You do not require a big 2D NOE spectrum and everything. You can do it by 1D NOE, steady state difference NOE experiment. We will start with this one. Let us say this is a spectrum of this molecule. There are only, this is a phenyl group. We are not worried about what is that and everything. This is the phenyl group. Basically, there is a CH2 proton, and these two are the protons, two protons, which is attached to that ring, okay, 5-membered ring. Now our doubt is, which is this proton? There are two here. There are two correspond to these two, HA and HP. One is HA, other is HB. Which is HA, which is HB? I do not know. I could make a mistake, because there is no way I can identify this. C6H5 is far away, I can identify this. CH2 is separately here, I can identify this. Then between these two protons, which is which? This specific assignment of the individual protons could be little bit problematic. All the molecule is very simple. Of course, there are ways to do that. You can go into take the nitrogen 15 HSQC, see the long range correlation, HMBC, long range correlation, etc. That is all okay. But in a simple way, one dimensional experiment if you want to do, to make the site specific assignment of this particular proton, what I will do a 1D steady state difference NOE experiment. I will irradiate this proton, CH2 proton is here, this is a normal spectrum, and then I take the difference after irradiating this, take the difference. When you take the difference, of course, this will be saturated, and there won't be any signal after saturation. So, the difference when you take this will be negative, that is what is happening. When you take a difference spectrum, the saturated peak won't be there when you saturate. So, when you take the difference in the normal spectrum, that will be a negative peak, huge intense negative peak will be there, that is what it is. This tells me I have saturated CH2 protons. This is okay, not a well resolved spectrum, it is a simple, little broad and clumsy spectrum, but this entire group of spectral lines, if at all is, even if it is resolved, it is attributed to phenyl group. Then what is left? These two. But if you see the difference NOE here, I saturate selectively this CH2 and take the difference. Of course, there is some change in the intensity for a phenyl group, that is okay. Some NOE is transferred to one of these protons of the phenyl group, that is expected, because it is close to, it is attached to phenyl group only. But then if you see carefully, this peak there is no change at all, it is not seen at all. But you will see there is a NOE for this proton. Which is that proton? This CH2 when you radiate, the close spatial proximity is this one. So it can give NOE only to this. With this idea, I can specifically assign this proton to HA. Very easy. So this is the assignment problem. If you need to make the assignment properly, even a small molecule. And why do you need a 2D NOC for this simple molecule? See, all you need to know is simple molecule. You have to identify CH2. Use your idea. If you use this selectively saturate CH2, if at all there is NOE, it has to be only for this. Then you make the specific assignment. So assignment problem can be solved. This is one way. So selective saturation CH2 clearly established this is a HA proton. Fine. I will give you a little difficult problem, in the sense little bit more complex. How do you distinguish two naphthalene structures by steady state NOE? What is this two naphthalene structure? Let us see this one. There are two naphthalene structures here. One is, see this group CH2CH3 is here, another is CH3 attached. There are two possible structures we can think of, A and B. What is A? In the case of A, this CH2CH3, Cl. CH2Cl is here. CH3 is this side. Whereas in the other case, CH3 is at this side, CH2Cl is here. There are two possible structures for this naphthalene substituted molecule. Our job is to find out, the challenge is which is the correct structure. We do not know. These are the two possibilities, and the NMR spectrum is taken. When once you take the NMR spectrum, first you have to make the assignment. Assignment is simple. Of course, this entire region is expanded here. If you expand, already I have told you how to assign the phenyl protons. These two are the exclusively two protons which experience only orthocoupling. Whether it is this molecule or this molecule, does not matter. There are only two protons which experience only one orthocoupling, and a large doublet will be there, which is that one. If you look at, and of course this we can assign CH3 proton, and this is CH2 which is attached to chlorine, so a little bit downfield. Fine. So assignment can be done. This aromatic proton, when you want to assign, I would say these two are for this phenyl ring. Fair enough, because these are the only two doublets with identical peak separation, and this must be from this phenyl group. In this phenyl group there are 4 protons, there are different multiplicity pattern you are going to see. So that there, if you see, these two protons will be more like a triplet structure. I told you 2 orthocouplings and 1 metacouplings. For this one, if you carefully see, these two protons, each one will experience 1 orthocoupling, 2 orthocouplings and 1 metacoupling, each of them. So as a consequence, it will be like a triplet of a doublet. So these two are these two protons, and of course remaining 2 protons here, 1 ortho, 1 meta and para coupling. In principle, each of them should be doublet of a doublet, 8-line pattern. Doesn't matter. We are not worried about multiplicity pattern at the moment. We can assign all those things very carefully. But I just want to assign these 4 protons belong to this phenyl group. Fair enough assignment. Okay. But our problem is whether CH3 is this side or CH3 is this side of the naphthalene ring. We will see that. So assignment, if this confirms, of course this type of assignment, one thing I can tell you, this type of assignment, if it is there, what are the possible structure for this? These 2 protons here, if I remove that, these 2 protons, these 2 substitutions should be ortho to each other. If not, other possibilities, it should be para to each other. Why? Only then there is a possibility of 2 protons experiencing orthocoupling. If it was meta, then we will have a metacoupling which is much smaller. Orthocoupling is quite larger, and there is only 1 orthocoupling for both of them. As a consequence, the first conclusion is these 2 substituents are ortho to each other or para to each other. One of the possibilities we can think of. It must be either ortho or para to each other. But para is ruled, of course para can be there, but we can rule it out by doing some difference 1D difference NOE experiment. What we will do is you selectively saturate CH2 proton. This is the molecular structure. Of course, these two, this is CH3 and you see this proton is enhanced. What is that proton? If you carefully see, this proton has been assigned. These two are for the one phenyl ring and these two for other phenyl ring. This, when you irradiate CH2, enhancement is seen at 8.13 ppm and also CH3 protons. When it can happen? This can happen only if you carefully see this. Let us look at this. This can happen if I am irradiating this CH2, you cannot get NOE for this. You can get NOE for CH3, that is correct, that is possibility is there. But for one of the phenyl protons, when there is NOE, it must be this, it is to the proton of the other ring, other phenyl ring, not where CH3 is attached. So, I would say this is the possible structure for this. This says enhancement of another proton is consistent with the structure. It cannot be this. Okay. If it is this, let us say, this can give to this one for this proton and not for other proton. See, assignment we have already done. So, it is not possible. This assignment is clearly known. So, obviously, if this is the structure only, you can get enhancement at this proton and enhancement for CH3. That is one conclusion. But we can further confirm it by doing selective irradiation of CH3 proton. CH3 is here. Selectively I saturate that. Now, when I do that, there is enhancement for CH2 and also there is enhancement for one of the protons at 7.34. This 7.34 proton, we know it is from this phenyl group, from the assignment we have already made. Understand? So, I saturate CH3, I am getting enhancement at CH2 and also at the phenyl proton. Then this cannot be the structure, because if I saturate this one, okay, CH3, I may get enhancement for this, NOE for this, but not for this. That is not possible. It can give for this, like we saw in the previous case. So it cannot give for this. Obviously, this must be the structure, because if you saturate the CH3, you get enhancement here and enhancement for CH2. Look at the structure here. We have saturated CH3, we are getting enhancement at CH2 and enhancement of one of the protons of this phenyl ring. So, that must be the structure. So, this irradiation of both CH2 and CH3 confirms, and this must be the correct structure of the molecule. You understand? Now, we could get the correct structure of the molecule. This is the way we could identify the substitution in the naphthalene rings. We can do another thing, the regiochemistry of two alkyl substituents of the pyridine ring I will see. This is the pyridine ring. Now, there are two possible structures given here. One is CH2 CH3 here and CH3 is here. This is the nitrogen. So, this is CH3 and this is CH2 CH3. Alternately, this is CH2 CH3, CH3 is here. Understand? CH3 could be between these two protons, or CH2 CH3 could be between these two protons. So, this is called 2-methyl 5-ethyl pyridine, or this is 2-ethyl 5-methyl pyridine. See, methyl pyridine, methyl ethyl pyridine or ethyl methyl pyridine. These are the two possible structures. How do you identify which is which? Okay. We will go for this. This is the NMR spectrum, and of course, there are only 3 protons. CH2 CH3 is here, we know that. CH3 here, CH2 here. Of course, which is methyl CH3, which is methyl CH2, you can identify. Okay, one CH3 is here, that is other one is CH2 CH3, it has to be quartet and triplet. This is from CH2 CH3 group. Other CH3 is here. Okay, fine. With this, this is more like a singlet. This is more like a singlet. So, so this has to be CH3 has to be a singlet. There is no way it can get coupling to anything, and long range coupling. So, this if it is CH3, it is a singlet. Also, we can make the assignment this CH3 singlet and CH2 and CH3 for the group. Methyl and ethyl group is assigned. Then what is left over? Phenyl group. In the phenyl group there are 3 protons. This is very easy to assign because consider this proton, this has only ortho coupling and para coupling. If it is not resolved, it is only simply a doublet. What is that possibility? You can look at it, there is a doublet here. This is possibly experience on ortho coupling and para coupling is not resolved. Whereas if you look at this proton H4, this experience ortho coupling with this and a meta coupling with this, it is going to be doublet of a doublet. So this is H4. What is left over? This one, and this one H6 has to be a doublet because it is coupled only to this. So based on this, assignment of all the 4 phenyl protons have been made with the knowledge of multiplicity pattern, everything. Now the question still remains is whether the ethyl group is there here R and R prime is methyl or ethyl. If R is ethyl, R prime has to be methyl. If R prime is methyl, other one has to be ethyl. So whether we have to find out what is what. What we will do is we will selectively do the inversion of one of the CH2 or selective saturation. We will do one of the protons. Which one? We are going to do the CH2. CH2 CH3 is there, you know. Selectively we invert one of the CH2 protons, CH2 protons of the CH2 CH3 group. That is done, selectively inverted. And NOE is done, difference NOE is taken. So this is the group, one normal spectrum and this is the different spectrum after selective irradiation. Where are we seeing the peaks? See, there is enhancement for H6, enhancement for H4 and there is enhancement for CH3 with some distortion because of the multiplicity. As I told you, if you do not exit the paper all the group properly, there is going to be a problem of anti-phasing. This is what I told you. In the multiplicity, you choose uniform perturbation should be there. Otherwise, this anti-phase character can nullify the intensity. But anyway, there is some distortion is there, but not so much. Let us consider the intensity enhancement. If you saturate CH2 proton, you are going to see the enhancement of H6 and H4 and also CH3. What is that possibility? Okay. This conclusion is ethyl group is located at the position 5 of the phenyl ring. This is the ethyl group, not methyl, because if CH2 is irradiated, only when these two are getting enhancement H4 and H6, it is possible only when ethyl is here. If it is ethyl is here, these two cannot get the enhancement. You understand? So that is rules out methyl here. So R has to be ethyl group containing CH2 and CH3. That is easy, very easily you can do that. So ethyl group is situated at the position 5 of the pyridine ring. Then obviously other one has to be methyl. To confirm further, you can do other experiments also. We saw enhancement at H4, H6, selectively irradiate H6. Obviously you must see the enhancement at CH2, this one CH2, you see that, and also CH3, very easy. So you could see that. So if selectively irradiate H6, you got enhancement for CH2 and this one. Similarly you do for H4, you are seeing enhancement for CH2, CH3 and of course some disturbance is there, but that neighboring peak is also getting this thing. This will also when you hit H4, this also get enhanced. That is okay. That is not our interest, but understand H4 gives correlation to this and this and also bit of CH3. That clearly confirms this CH2 CH3 is next to each other. It is not on this side of the pyridine ring. Okay. Further what you can do is you can also do irradiation of the CH3 H3 proton here. If you do H3 proton, where do you expect the enhancement? It has to be only this and this, nothing else. None of these should get the enhancement. Exactly. You see this. You are irradiating this, selective saturation of H3 gives you enhancement for H4 proton and also for this CH3 proton and bit of disturbance for other things. Okay, that is not important. Most important is H4 and CH3. These are enhanced because of hitting CH3 proton. What does it tell you? This tells me CH3 has to be on the other side of this side next to nitrogen. So, this must be methyl, this must be methyl. So, different NOE experiment, selective NOE confirms which is the isomer which you are looking at, whether it R group is methyl or ethyl, we can easily identify. Okay. We can do one take a little complicated molecule. In principle, for this you require 2D NOC, but I can tell you sometimes even in such big molecules, even simple NOC, one dimensional difference NOE can also help. And there are, we are considering the molecule thujone. Thujone has two isomers, alpha and beta. What is that alpha and beta? This is alpha, this is beta. In the case of alpha, what will happen is C6 is a gamma carbon. These have both Gaussian and anti relationships there. That means once proton H4 proton is here, other case H4 proton is opposite, CH3 is here. See, CH3 and H4 proton position gets changed for alpha and beta thujones. In the alpha thujone, H4 is close to endo, say H6 endo, whereas in beta thujone CH3 is close to endo, H6 endo. These are the only two conformational changes you can notice. Then it is easy. If you identify what is H6, simply do the selective radiation of that, do the NOE, selective NOE. Then if you find out whether the enhancement is on the CH3 proton or H4 proton, then you know whether it is alpha thujone or beta thujone. Very easily we can do that. And this is alpha thujone. In this case, we have C6, C10 are on the same side of the 5-membered ring, C6 and C10. Both are on the, on the opposite side of the C6 is here and C10 is here, opposite CH3. They are on the opposite side of the 5-membered ring. Whereas in the beta thujone, of course C6 and C10 here, they are on the C6 and C10, they are on the same side. See, they are on the same side of the 5-membered ring. In the previous case, they are opposite each other. C6 is this side, C10 is below, okay, opposite side. Now of course we can also do the, of course mind you, in the carbon 13 NMR also gives you a lot of information about the isomers, stereoisomers. Although I did not explicitly tell you, the carbon 13 chemical shift can also be used to get the stereoisomer information. For example, in the alpha thujone and beta thujone, if you consider, see these protons, these protons 6 and 10, especially in beta thujone, are shifted quite a bit by 4 to 6 ppm. Similarly, this proton 4 and 5 are also shifted. This is because of steric hindrance there, steric clash is there between C6 and T10, and that will push these carbons a little far away. Similarly, for C4 and C5, it pushes to high field. Both these carbons compared to alpha thujone, they are moved high field because of steric clash. Of course, if you go to the carbon 13 NMR very, very carefully, there is a lot of things to discuss. Then you can also get the information about isomers by looking at the chemical shift information. Chemical shift also tells you based on how much it has moved high field or low field, some idea. If we need some expertise on that, you can also get information. Okay, assuming that we are not interested, we do not know that much, we want to observe only 1D selective NOE and see that. In the NOE, here what we can do, we can selectively invert the 6 endo here, 6 endo, not exo, 6 endo peak in thujone. You do not know which is which, does not matter. We will take that, then both could be 6 endo. When you invert, take the look at the NOE position for H4 and H10, that is what I told you. If there is enhancement for H10, then it is beta. If there is enhancement at H4, it is alpha. Very easily you can do selective NOE. You do not need to go for 2D NOE for this. So, alpha thujone should go a very strong peak for H4 and weak NOE pass for methyl H10, for this very weak. Converse is the case for beta thujone. So, beta will give strong NOE for this one and weak NOE for this one. You see the distance matters, distance is less than 5 angstroms here, okay. This is 3.1, this is nearly 4, that makes the difference. Okay, we will see that how this experiment is done. This is selective NOE and one of the diastereomer. I do not know whether alpha or beta. Some molecule has been chosen that is alpha or beta I do not know. This is a normal one dimensional spectrum, and selective inversion is done for 6 endo. Assuming that assignment has been done by using COSI or using your knowledge of multiplicity pattern, everything which can be done. You simply by using COSI you can make the assignment. Especially XO and endo, one important thing is in the sugar molecules like this, what you should remember is XO will be always downfield and endo will be in the high field, and the XO to XO coupling, J coupling between XO is much larger. Here you can see splitting is much larger than this one, but remember XO will be little downfield compared to endo. Not always true, but most of the time you can identify that. So now 6 endo is here selectively inverted, and this is the difference spectrum. See what is the difference? There is enhancement for proton 4, large enhancement. Where is proton 10? Very small, that is a distorted one. And another enhancement is proton 5. And I have 6 XO. Of course, when you hit 6 endo, 6 XO has to have enhancement because they are just they are geminal protons. So obviously, if you hit one, other one has a strong enhancement. That is not an important thing. But what is important is H4 has a very strong NOE. Okay, this is what it is, very strong NOE. H10 also is there, bit of distorted one. So largest NOE for H6 XO because of geminal distance, and NOE for H2 endo is also there, and H4 proton is large because the distance is very small. A strong NOE for H4 peak and a weak for H10 confirms this is alpha thujone. That is what I told you. So I did not know the molecule, I did not know the alpha or beta, but I knew by the structure if I hit 6 endo, H4 if it is intense, NOE is stronger there, that must be alpha. Otherwise if H10 is stronger, that is beta. Okay, we will confirm that. The fourth NOE peak is something H5, that all not important for us. Now from this NOE experiment you can conclude H4 is on the endo phase of the 5-membered ring close to 6 endo, and H10 methyl group on the XO phase far from X endo. Obviously this sample is alpha thujone and not beta thujone because of the NOE. H4 is on the endo phase of the 5-membered ring, that is very close to H6 endo, and the H10 is other side, XO side. Because of that we can say it is a alpha isomer. Now we will take other stereoisomer. Same thing, I do not know which one which. Now what we will do, the selective irradiation of 6 endo again and take the difference here. What is that you are seeing? You see the enhancement for 2 endo, and of course 6 endo is always XO is known because they have a geminal relationship. Another important thing is you will see enhancement for proton 10. Of course there is antiphase relationship because of some issue here, does not matter, but you can see enhancement is more for H10 and little bit for 8, 9, and major is there for 2 endo. So look at this, largest NOE for this H6XO is 0.76%. A strong NOE for H2 endo is also revealed. Okay, and then a strong NOE combined with the subtraction artifact is observed for H10. Subtraction artifact is 2 multiplets are positive, 2 multiplets are negative in intensity. It could be subtraction artifact, or it could be because of improper excitation multiplets, we do not know, but there is an artifact, it does not matter, but still it gives a largest NOE for that. So what is the conclusion? H4 is on the XO phase of the 5-membered ring, H4 far away from endo, and the H10 H methyl is on the endo phase close to 6 H6 endo. That shows the sample is beta thujone and not alpha thujone. Very easily you could distinguish two isomers, alpha and beta isomers, thujones, by just doing selective NOE experiment. So this is what I wanted to tell you about this thing. Now that since the time is getting up, what I am going to do is I will stop now. I will continue with 1 or 2 more examples of where do you apply selective NOE, 1D selective NOE, so that you can get the conformational information. I took simple molecule and then slowly we went to a little bit bigger molecule. In this class what we understood is selective irradiation of one of the protons you could identify close spatial proximity of other protons and get confirmation whether it is cis or trans, and EZ geometric isomers we can identify. There are lots of experiments we can do. Only thing is, the requirement is frequency selective excitation has to be proper, otherwise you will be distorting. There is a leakage of the frequency. If you selectively excite neighboring protons, then it could be confusing. And we also found out we can identify isomers and regiospecificity depending upon the substitution of the phenyl group, whether it is which place the substitution is present. And in the regiospecificity we substitution we understood whether the methyl or ethyl group and whether it is which side of the pyridine ring also we understood. All this because simple one dimensional difference NOE experiment. The conclusion is you do not need to go for a 2D NOC, a big experiment and spend lot of instrument time and more time, and then to get into that. Instead of that, if your molecule is simple, just by looking at it you know which to irradiate, simply do the one dimensional difference NOE, you will get the structural information. So with this I am going to stop here. In the next class we will continue with one or maybe one example, another example where we can get different type of information, and then we will go to a different type of one dimensional experiment. Thank you very much.